Hello everybody, and welcome to Lecture 8 of our Calculus 1 course. So, yesterday I said we were going to work on inverting some of the differentiation rules in order to get integration rules. And I said that we were first going to reverse the product rule and then the chain rule, but then I decided that it would make more sense to start with inverting the chain rule. So that's what we're going to do today. And then on top of that, we're going to have a little twist, which is called substitution, which is a different sense of reversing, because we like to reverse everything in this class other than don't listen to the Hotel California in reverse. So I'll start, motivate the whole idea and give a little preview by starting with an example. So say we want to integrate x over the square root of x squared plus 1, starting from 0 and going up to 3. Sorry, going up to, going up to 3. That was ahead. And so this, you might think that this should be the derivative of something. If we look at it, we can see some sort of chain rule type of thing going on. This is kind of like the derivative of x squared. So we could write 1/2 1 over the square root of x squared plus 1, and then times 2x, because we're now making it the derivative of x squared. And then now we can see the chain rule is really coming into play. This integrand here equals the derivative. It equals g prime of x squared plus 1 times x squared plus 1 prime. And so this right here, this is d over, I should say what g is first, where g of u equals the square root of u, right? Because the derivative of this is 1 over twice the square root of u. And so this whole thing equals d over dx of the square root of x squared plus 1. Therefore, this is the integral. This integral is this quantity, this function. And so the integral is square root of 3 squared plus 1 minus the square root of 0 squared plus 1, and that's just going to be the square root of 10 minus 1. Now, what we've just done here has the essential features and is in fact what we're going to be talking about more generally, which is called u substitution, which is the inverse of the chain rule, as I've said. And so what does the rule say? The u substitution rule, well, it says that, well, first of all, I'll write the chain rule for reference. So f of g of x prime equals f prime g of x times g prime of x. And so if we have integral f prime of g of x times g prime of x dx, indefinite integral here, this is just going to be f of g of x, because it's the thing that has this. The indefinite integral is going to be the thing that has this as its derivative, but that's going to be exactly this, because the chain rule, we're just doing the chain rule in reverse. So that is that, and yeah, so the first example I gave might seem a little contrived. You know, we sort of made the derivative appear in some sense, the x, but this really is fairly useful. I'll give you a little example. So let's consider an example. Secant to the fourth theta d theta. We want to find the antiderivative of this. So we know that secant squared is the derivative of tangent, and secant squared can also be expressed in terms of tangent. So this might seem like it's sort of coming out of nowhere, but it's not really. I mean, it's good to have trig identities on your fingertips, like that tangent squared plus 1 equals secant squared. Of course, you're probably more comfortable, maybe you're super comfortable with both of them, hopefully, but if you're not comfortable with that one, you're probably already comfortable with cos squared theta plus sine squared theta equals 1. Those are both important ones to be ready to carry around any time. And of course, cotangent squared theta plus 1 equals cosecant squared theta. That's a good one too. So secant to the fourth theta, we can divide it up into a function of tangent theta and the derivative of tangent theta, which is the whole idea of this inverting the chain rule business. So one of the copies of secant squared theta becomes 1 plus tangent squared theta. We turn it into that, and then the other one, of course, becomes the derivative of tangent theta. So we could write this as f of tangent theta, where f of u equals 1 plus u squared. And so now we just need some function f, capital F, of u with f prime, big F prime of u equals little f of u. And this function is going to be none other than the integral of f of u du. And and that's what this is going to be. It's going to be this function f of u, but then we're going to put tangent of theta in for u at the end of the process. If we were to do a definite integral, we would need to worry about the endpoints, and I'll get there soon. But so this integral right here is this integral. So the way that we often write this is tangent theta equals u, and then this whole thing equals du. And that's how this becomes this. Sort of a notational matter, I guess you could say, but so this integral of 1 plus u squared du, we talked about inverting the power rule yesterday, and the power rule we have for integration. So this is going to be u plus u cubed over 3 And so the way it works in terms of bounds, so let's throw some bounds on here. So let's say we're going from 0 to pi over 4, 0 to pi over 4 for theta. So then when we turn into u, we need to do tangent of u. When we transform into u equals tangent theta, we need to put in tangent of, that's going to be the bounds for u. So we need to put in tangent of 0 and tangent of pi over 4. And our bounds down here. I'm going to erase this so we get it white out. And so tangent of 0 is just 0. And then tangent of pi over 4 is just 1. So these bounds are just 0 to 1. And the way that we oftentimes denote this for evaluating definite integrals when we've got to this point is we just have a vertical bar and we put a 1 at the top and a 0 at the bottom. And this says to evaluate this at 1 and then subtract this evaluated at 0. So we're going to get 1 plus 1 cubed, which is still 1 over 3, minus 0 plus 0 cubed, that's just 0. And this is going to equal 4/3. So that is our final answer for the integral of secant to the 4th from 0 to pi over 4. And this example, I guess it's sort of secant to the 4th. It sort of seems like it comes from the wild. Seems a little bit less contrived than just writing in a multiplicative factor that's clearly the derivative. But the thing with integration problems is you never know if you're going to be able to solve them or not, which is sort of frustration as opposed to the derivative. Like, I give you any sort of function and you just use the derivative rules and you can find the derivative. Any of the functions we talk about in this class, I just give you the function, you can find the derivative, and there's no question in advance if you're going to be able to find the derivative. So that's kind of nice. With integrals, that's not true. We just have catalog of tricks that apply to certain situations, and so we may or may not have a trick. If someone would just throw a situation at you, we may or may not have a trick to solve it. As we expand our catalog of tricks, we'll feel more and more like we can actually just go out there and evaluate an integral. But of course, there still will be things that we can't do. But so, for example, this one, if we made it secant to the 5th, then we would no longer have something that could conveniently be solved by the same type of thing we're doing. So it is sort of contrived. It's like, okay, here's something that we can solve with this particular method. But it could be evaluated, and we'll get to the methods that can be used to evaluate this later on, maybe today, but probably next time. But there are integrals that you can't find a nice antiderivative function for. So like, for example, sine of theta squared. There isn't a good antiderivative function for this. Of course, if we put bounds on this, like 0 to pi over 2, or 0 to the square root of pi over 2, this is just going to be the area under some curve. And so there is some area. I mean, you can graph it, and you can say, well, it's just that area that's in the picture. And it would be something like this. You could say, well, it's just the area in the picture, so the integral certainly exists, and it does. It's just a question of whether or not you can find an indefinite integral. But sure enough, the area still exists. So that's, I guess, just a qualifier on integration and how universally we can solve problems. So the problems that I'm presenting for any given method is kind of like, okay, is this a problem that we can solve by this method? So the problems I'm presenting are somewhat catered to being able to solve them. And let me restate what I said about tangent in a more abstract form. So for definite integrals, the integral from a to b of f g of x times g prime of x dx equals integral of f of u du, and what are the bounds going to be? Well, I told you before, but let's build it up this time. So we of course know that this is going to be the final function, where f prime, or sorry, capital F of u, its derivative equals f of u. So, but what are the bounds? Well, we look at this. This capital F is, of course, the antiderivative, the indefinite integral. And so the bounds here are going to be, the upper bound is going to be g of b, the lower bound is going to be g of a, g of b, g of a. So this is the rule for evaluating indefinite integrals. And then again, to reiterate, in our last example, this was 0 to pi over 4, 1 plus tangent squared theta. Tangent of theta is g, and then tangent theta prime d theta equals integral tangent 0 to tangent pi over 4 of 1 plus u squared du. Replace tangent theta with u. Okay, so there's a couple somewhat fancy applications of u substitution. So let's look at some fairly trivial applications of u substitution. So integral of f of x minus c dx, c is some constant shift factor. This we can set equal to u, and then du is going to be the derivative of x minus c times dx, because remember we use this notation that I erased it now. I should have made more of a comment when it was up. Maybe I'll rewind and make a comment about this, that when we have integral f of g of x times g prime of x dx, we call this term du, and this u. So g prime of x equals du. So that being said, let's go back to the application here. So the integral of f of x minus c dx so x minus c is going to be u, and then du equals the derivative of x minus c times dx, but this of course is just 1, so du equals dx. So we can immediately just turn this into, in bounds of integration a to b, we can immediately just turn this into a minus c to a minus b of f of u du. So that's one fairly trivial application, and then another is integral a to b f of cx dx equals 1 over c times integral ca to cb of f of u du. This just again comes from the fact that f, I'll use a capital F, that f prime of c, it's hard to distinguish c's from parentheses sometimes, f prime of c, sorry, f of c of u whole expression derivative equals c times f prime of c by the chain rule, and that gives us this rule because we're doing differentiation in reverse. Now we have 1 over c instead of just c. So let me give a little example which uses some fairly trivial rules but then arrives at a conclusion that's actually somewhat of interest and or somewhat non-obvious perhaps at first. And so integral from 0 to 3 of x over the square root of x plus 1 dx. So this looks like the example from before, but now this x is not squared anymore, so it's not the straight up substitution deal anymore. But we can say, you know, I don't really care for having expression inside of the square root that's anything other than just a variable. So let's make that expression the variable itself. So let's say u equals x plus 1. Then we have the integral from 1 to 4. So u equals x plus 1. Now we have the integral from 1 to 4 of, so u equals x plus 1 implies that x equals u minus 1. So this is going to be now u minus 1 over square root of u du. This is going to be integral from 1 to 4 of, we can now distribute the multiplication around. So it's going to be u over the square root of u, which is just the square root of u, minus 1 over the square root of u, u. And so this, we're going to have the integral of the square root of u, which is really u to the 1/2. So we could write this u to the 1/2, u to the minus 1/2. And then, as I mentioned yesterday, we have this inverse of the power rule that we can use, this power rule for integrals, which is going to give us u to the 1/2 plus 1 over 1/2 plus 1 plus u to the minus 1/2 plus 1 over minus 1/2 plus 1. Evaluated, I'm using the vertical bar notation here again, evaluated from 4 and 1. And so this we can rewrite as u to the 3/2 over 3/2, so that's going to be 2/3 u to the 3/2 plus, this is going to be 1/2 in the denominator, and this up here, this is just going to be u to the 1/2. So plus 2, right? 1/2 in the denominator becomes 2 in the numerator. 2 u to the 1/2, evaluated from 4 and 1. So at 4, we're going to have 2/3 times 4 to the 3/2. 4 to the 3/2 is the square root of 4 cubed, which is going to be 8. 8 plus twice the square root of 4, 2 times 2 is 4. And then we want to get it all over a common denominator. So we're going to have 16 over 3, 2 times 8, 16 over 3 plus 4 times 3 over 3 to get it over a common denominator, so plus 12 all over 3, and we get 28 over 3. So there's an example of that rule, and so now I'll give you some different notation in the Leibniz notation for all of this, which again has a certain appeal, as all the notation that Leibniz has introduced in general tends to be appealing. But so we can write this integral of f of u of x du over dx. Right, this is our archetypal u substitution expression, and this has the appealing feature that you can just, that it's like canceling the dx's in the fraction. So this becomes just f of u du. It's like you're canceling the dx's with each other. And if you think in terms of infinitesimals and the rectangles, like I talked about yesterday, there you can sort of interpret this, I guess, in those terms. So yeah, but another thing that you could do is we could do this whole thing in reverse again. As I said, reversing something that's sort of reversed, but not getting back to the original. We're not talking about differentiation anymore, but this is a different sort of reversal. So in this reversal, it's called substitution. It's usually trig substitution, but then we're also going to do hyperbolic trig substitution, which I touched on hyperbolic trig 2 days ago, and I'll give a bit of a refresher on it before we do any substitution problems with it. But first, I'll introduce substitution and then do a trig substitution example. So we have integral of f of x dx. We could then go in the opposite direction and say, okay, well, I want to express x as something else. So we could say integral, so I'm going to insist that x be a function of t. So then we could turn dx into dx over dt times dt. So you could ask, why on earth, why in the heavens would we do this? And I'll give you an example that will illustrate why we might do this. So let's say we wanted to find the area of a semicircle up to a given point x. This is x. And if we wanted to find the area, so this area over here, so this area is going to be the integral, this a of x, the area of the slice of the semicircle going up to x, starting on the left end and going up to x, is going to be integral from -1, this is the unit circle, so this point is -1, integral from -1 up to x of this curve. So this curve is 1 minus square root of 1 minus x squared dx. And you know what, let's say that we wanted to do the whole circle, segment of the whole circle rather than a semicircle. So what does that change? Well, it just multiplies it by 2, because we just have the mirror image of what's up here. Whatever this area is going to be the same. So we just multiply the whole thing by 2. So, okay, so substitution. So then let's say, so this square root of 1 minus x squared is, what do we do with it? But something we can do with it is we can do this reverse substitution where we say x of, how should I write this? You can say x of t x of t equals cosine of t. And then if we do that, this just becomes sine t, which I mean sort of makes sense because sine t is often the y-coordinate on the circle anyways. So, of course, you know, x is, of course, the cosine. So this is very natural in this geometric picture. You can also imagine a trig substitution somewhat in a less pictorial setting, but when you see this expression, it could be useful to a trig substitution. But anyways, getting back to this, so this becomes, we do x of t equals cosine t, so we get 1 minus cosine. In this case, let's just call it theta because I mean we're just dealing with this unit circle. It even is going to be the angle. You can interpret it that way. So 1 minus cosine theta squared, 1 minus cosine theta squared, and then dx. dx equals the derivative of cosine theta, which is minus sine theta, then times d theta. So this is dx. And so this whole expression here, I'm going to erase this now, but keep it in mind. So this whole expression here, this is the square root of sine squared theta. This whole expression is going to become negative 2 times integral of sine squared theta d theta. Oh, great. Well, how do we evaluate the integral of sine squared theta d theta? I haven't really introduced so far any rule from which it would be obvious how to evaluate this. But there are these formulas from trigonometry. Like I said, you know, it's good to have formulas from trigonometry on your fingertips. Of course, this is an online class, so you can always just look them up, I guess. But it's good to know them. They're good, they're fun, they're cool, they're nice. And the formula that we use when integrating this is the formula that cosine of 2 theta equals cosine squared theta minus sine squared theta. And of course, we also know that 1 equals cosine squared theta plus sine squared theta. And so if we add these two equations together, or actually we have sine here, so let's subtract this equation from this equation. So if we subtract this equation from this equation, we're doing that to try to get sine squared in terms of these things. So 1 minus cosine 2 theta, 1 minus cosine 2 theta equals 2 sine theta, or sorry, 2 sine squared theta. 2 sine squared theta. And so then if we just multiply this by 1/2, then we have sine squared theta. Of course, this is something that we can evaluate with the sort of trivial rule that I was just telling you about. So that's the whole point of doing this substitution business, is it allows us to use a rule that we know how to apply. So okay, so this equals negative 2 times integral 1/2 1 minus cosine 2 theta d theta. Of course, these two 2's, I shouldn't put that across the integral bar, but this 2 cancels with this 1/2, of course, and we end up with negative the integral 1 minus cosine theta d theta. And if you notice, I haven't put bounds on this integral, and the reason that I haven't put bounds on it is, you know, I didn't put bounds here, and we could put bounds here, but the reason I didn't put bounds is that at the end we're going to reverse the substitution, because I mean the bounds, they would just be, we would use inverse functions, right? We would use cosine inverse, so we'd have cosine inverse of -1, this would be negative pi, and then cosine inverse of x, but it's just sort of annoying to carry around all those cosine inverses. And then at the end we're going to plug in x equals cosine theta back into the expression, so no need to be carrying it around. But so, some more space. So this integral equals negative integral, sorry, we can go ahead and evaluate the integral. So this is going to be negative theta, right? Because you integrate 1 d theta, you just get negative theta. And then minus, so plus the integral of cosine 2 theta. But the integral of cosine 2 theta, by the rule that we mentioned before, it's just going to be 1/2 of the integral of cosine theta. And the integral of cosine theta is the thing that has cosine theta as its derivative. It's going to be sine theta. So this is going to be plus 1/2 of sine theta. Sorry, sine 2 theta. And this is all, evaluated. And as I said, evaluated from cosine inverse of x, and then cosine inverse of -1, which is negative pi. Sorry, positive pi. I guess, it could be either one, but let's go with positive pi. So this is going to be negative, the theta here, we're going to have negative cosine inverse of x minus negative pi. So negative cosine inverse of x minus negative pi. And then for this other term, we're going to have 1/2 of sine 2 theta. And okay, so this is where we're going to have to pull in another trig identity. So this problem seems a little bit complicated, but it's actually, just a lot of step-by-step stuff. So sine 2 theta equals 2 times sine theta times cosine theta, or let's write it in reverse, cosine theta times sine theta. And if x equals cosine theta, then this is just going to be 2x times 1 minus the square root of x squared, right? Because sine theta is then going to be, if cosine theta equals x, then sine theta is going to be the square root of 1 minus x squared. Technically plus or minus, but since we're dealing with this upper half of it, it's going to be plus. And so this is going to be 1/2 of sine 2 theta evaluated up top here. And so that's going to be 1/2 of 2x times the square root of 1 minus x squared. And then minus, it's evaluated down at the bottom at pi. Well, at pi, sine of theta is 0. This is just going to be 0. And so our final answer, these 2's cancel. And there's no 0 anymore. And minus negative pi just becomes plus pi. So this is our final answer. And, oftentimes it's good to check your work by plugging in a known value. Like, if this is true, it should align with the things I already know. And something that we already know is that the area of the whole thing, the whole circle, is going to be pi r squared. R is 1. And for this circle, so it's just going to be pi. So if we plug in x equals pi, if we plug in x equals 1, so integrating all the way from -1 up to 1, the whole thing. If we plug in x equals 1, we better get pi. Well, cosine inverse of 1 is 0, so if x equals 1, this term disappears. And the square root of 1 minus 1 squared is 0, so sure enough, we're left with only pi. So that's good. It lines up with what we would expect it to be. So let's do another example of trig substitution, this time to find a different area, and that area that I'm going to propose to find now is the area under a hyperbola up to a given point x, in particular a unit hyperbola, which is the hyperbola that we have been speaking of, up to the point x. The hyperbola x squared minus y squared equals 1. So the area, so this curve right here, we can switch this around and note that y is going to be positive because this is above the x-axis. Of course, we have this curve also goes down here and it also goes over here. We're just looking for the area of this one. We could easily multiply it times 2 if we wanted to have this whole area, and then multiply it times 4 if we wanted to have this as well. So let's just look for this area, and that's in the first quadrant. And so this curve in the first quadrant is given by y equals, add y to both sides, subtract 1, take the square root, so y equals the square root of x squared minus 1. And so this area, A, we're going to have A of x equals the integral from, this is 1, this right here, this is x equals 1. So it equals the integral from 1 up to x of the square root of v squared minus 1 dv. And so you may get the sense we're talking about the hyperbola. I talked about the hyperbolic trig functions. You might think, well, we could use those, and that actually is a good idea. But first, I'm gonna propose to try to do it with trig functions, because if you think about it, with circular trig functions, as we may now call them, the familiar good old trig functions, because if you think about it, tangent and secant actually lie on a hyperbola, on this hyperbola, because secant squared theta minus tangent squared theta equals 1. So secant be x, tangent be y, and we're on the hyperbola. So we can do that substitution in here. We can make v equal to secant squared theta, right? Then we have secant squared theta minus 1 equals tangent, and then the whole shebang. So this is going to be the integral of square root of secant squared theta minus 1 times dv now is going to be the derivative of secant is going to be secant theta times tangent theta d theta. And so this is going to be integral of tangent squared theta times secant theta d theta. And of course, I mean, we could noodle around with this, and we could go some different directions noodling around with this, but we ultimately wouldn't be able to finish it without using methods that we're going to talk about next time, namely integration by parts. But you know, we could noodle a little bit. So this is integral secant squared theta minus 1 secant squared theta. Theta minus 1 times secant theta d theta. This equals integral of secant cubed theta minus secant theta d theta. And secant cubed theta, the integral of secant cubed theta is something that we're going to evaluate next time, but we don't yet have the tools to evaluate. You can think about it a little bit if you want. Try applying the methods that we've developed so far. See if you can evaluate the integral of secant cubed theta. It probably won't work out. I mean, there's all sorts of ways of guessing what what function could have a certain derivative, but I think the methods to do it are really going to involve the product rule, and we're going to talk about that tomorrow. But then integrating secant of theta. So okay, so we're going to return to this area of a hyperbola problem at the end of this lecture. Hopefully, at the end of this lecture if there's time. But I'm going to go on a couple of sides before we return to it. First, I'm going to talk about the integral of secant theta, and then I'm going to talk about the hyperbolic trig functions in some more detail, and then we're going to come back and we're going to tackle this same problem with the hyperbolic trig functions, and we're going to see that it works out more easily, and that it gives us some cool stuff along the way. So this attempt was ultimately unsuccessful because we can't evaluate this, and we can evaluate this, and I'll show you how. And it's pretty much boils down to making a good guess. There are maybe systematic ways of thinking about it that are more complicated, but the good guess way of thinking about it is fairly straightforward. And the good guess comes from the fact that, okay, so secant theta plus tangent theta, you take the derivative of this, and you get secant squared theta, or sorry, I should write them in the same order. You get secant theta tangent theta plus secant squared theta, and you can factor out secant. You get secant theta times secant theta plus tangent theta. So the gears may be beginning to turn. We can use the chain rule type of deal to eliminate this term, and that can be achieved through the natural log. So ln of secant theta plus tangent theta, the derivative of this equals 1 over secant theta plus tangent theta. Times the derivative of secant theta plus tangent theta, secant theta plus tangent theta prime. But this derivative is none other than secant theta times secant theta plus tangent theta. So they just cancel, and we end up with secant theta. Remember this prime, this would be 1 if we ignore this prime, but we can't ignore the prime, so it's secant theta. Plugging back in this expression for this expression for this whole derivative thing. So we get secant theta, so the derivative of natural log of secant theta plus tangent theta is secant theta. Okay. So now we know how to integrate secant theta, and I'll summarize it. I'll summarize this statement in the integral form, integral interpretation, which is that the integral of secant theta d theta equals the natural log of secant theta plus tangent theta. So there we go. So there we got a way of integrating secant theta. And now, as promised, let's talk a bit about the hyperbolic trig functions. And actually, before I talk about the hyperbolic trig functions, let me write over here on this side. I won't be writing on this side. Let me write some rules for reference and comparison, some rules for the circular trig functions that you may know, hopefully you know, maybe you don't. Now you do, now you will, presently. So, of course, the most obvious one, sine squared theta plus cosine squared theta equals 1, and tangent squared theta plus 1 equals, or let's write it as secant squared theta, the way I just wrote it earlier in this lecture, secant squared theta minus tangent squared theta equals 1. And sine of 2 theta, I alluded to before, sine of 2 theta equals 2 sine theta cosine theta. Cosine 2 theta equals cosine squared theta minus sine squared theta. In fact, the list goes on. There's all sorts of other formulas. This is a special case of the angle sum formulas, and then there's the angle sum product formula, and the tangent angle addition formula, and the half angle formula, which is just the inverse of this. But anyway, so there's lots of formulas, but I'm just going to stick with some more essential ones. So these are like these formulas relating different trig functions to each other, and then let's write some derivative rules as well, and let's just keep it simple, stick with the most simple ones. So sine derivative of sine theta equals cosine theta, and the derivative of cosine theta equals negative sine theta. And of course, these have corresponding integration rules that I won't even write because they're immediately derived from those rules. Or sure, I'll write them. So I'll write this small one. So sine. So derivative of sine theta equals cosine theta. And so this, as an integration rule, is the integral of cosine theta equals sine theta. Equals sine theta. And then derivative of cosine theta equals negative sine theta. And so then multiplying both sides of this equation by -1 and interpreting it as an integral, we have that the integral of sine theta equals minus cosine theta. Okay, so just a refresher on these relations, and now I'm gonna demonstrate some similar relations for hyperbolic trig functions. So, as I mentioned a few days ago, one of the sort of most essential relations is a hyperbola relation, which is that cosh squared t minus sinh squared t equals 1. In case you're wondering if there's something that corresponds to this, there in fact is. I'm not going to dwell on that yet. I'm not sure if I'll talk about it later or not, but I guess I'll go ahead and write it just for kicks. There's hyperbolic tangents and hyperbolic secant, which are defined exactly the same way as secant and tangent in triangular or in circular trigonometry. Is just sech t equals 1 over cosh t, and tanh t equals 1 over, or equals sinh t over cosh t. And then indeed you can it's not hard to prove this relation using these identities. But we're not really going to talk much about that yet, but it's kind of interesting because it shows that these things both lie on a circle and these things both lie on a hyperbola. But then, so let's drive a corresponding formula for sinh 2t. So sinh 2t, recall from yesterday, sinh 2t is going to be, or from the day before yesterday rather, sinh 2t is going to be e to the 2t minus e to the minus 2t over 2. And this, of course, is e to the t squared minus e to the minus t squared all over 2. And of course, algebra, we can factor this. So we can then factor this out. E to the t minus e to the minus t. And I'm just doing a 2 over 2 here for reasons that will soon be apparent. So we're going to have another 2. So we have 1 2 in the numerator, 2 2's in the denominator. That corresponds to just having 1 2 in the denominator, nothing in the numerator. But then doing this factoring, e to the t plus e to the minus t. And this, of course, is 2 sinh t times cosh t. So 2 times sinh t times cosh t. So sinh 2t equals 2 sinh t times cosh t. This is actually easier to prove than it is for the circular sine and cosine. So that's kind of cool. Then you might ask if the cosine formula is going to be the same. It's not quite the same. It's going to be a little bit different. Oh, maybe I shouldn't have said that. It's just a little bit of a spoiler. But so we're going to derive it now. So cosine. So the hyperbolic cosine cosh 2t. And actually, I prefer. So maybe the spoiler is okay. Because it sort of is preferable to write it in the opposite direction. So I claim what it's going to be is cosh squared t plus instead of minus now. Because if it was minus, it would just always be 1. And that wouldn't be okay. But so it's cosh squared t plus sinh squared t. And let's see why this is. So this equals e to the t plus e to the minus t over 2 squared plus e to the t minus e to the minus t over 2 squared. And this equals, we can gather together terms here a little bit. We have e to the 2t, e to the 2t, and then, sorry, I'm going to write down here. I'm going to make these 2's a little smaller, make some space. So we get, everything's going to be over 4. And we get a e to the 2t from this being squared, e to the 2t plus twice the product of these two things, right? Just foiling basic algebra. But e to the t times e to the minus t is 1, so we just get 2 times 1. And then plus e to the minus 2t, that's minus e to the minus t squared, right? And then plus, over here, we have e to the 2t again. Only now when we FOIL this out, we have minus 2 e to the t times e to the minus t, which is just going to be e to the t times e to the minus t is 1, so 2 times 1 is just 2. And then plus, finish the foiling, plus e to the minus 2t. And then this 2 is added and this 2 is subtracted, so they cancel out. And we're left with e to the 2t plus e to the 2t plus e to the minus t plus e to the minus t. So we group these things together and we get, we have a factor of 2 on e to the t and on e to the 2t and e to the minus 2t. So we have 2 e to the 2t plus 2. And so let's just erase, cross out these and put a 2 onto here. Well, then we cancel the 2 with a 2 in the denominator, so we get e to the 2t plus e to the minus 2t over 2, and that's just going to be cosh of 2t, as was asserted. So it's just going to be, as asserted, cosh squared t plus sum squared t. Yeah, and so we have corresponding rules for those, and so now taking derivatives, I claim, is going to be a walk in the park, much easier than taking the derivatives of sine and cosine as we did before. So sinh prime t equals sinh prime t equals the derivative of e to the t minus e to the minus t over 2. So the derivative of e to the t, derivative of all this, the derivative of e to the t is just going to remain e to the t. So of course we're all over 2, e to the t, and then the derivative of e to the minus t, minus sign is going to come down, so it's going to be plus e to the minus t, and this is of course cosh t. So the derivative of sinh t is cosh t. So that's very much like with sine. Derivative of sinh t is cosh t. And this of course gives us the rule that integral of cosh t equals sinh t. Definite integral there. And the derivative of cosh t is the derivative of e to the t plus e to the minus t all over 2. Derivative of that, so this of course is e to the, still all over 2, e to the t minus e to the minus t, which is of course nothing other than sinh t. So this is sinh t. Derivative of cosh t is sinh t. So now we don't even, it's even simpler than the rule over here because we don't have a minus sign even. Simpler to derive and a simpler fact. So then this implies that the integral of sinh t is, oh, I forgot to put an h right here. This is sinh t. Then the integral of sinh t is cosh t. So yeah, so there we go. So you might even want to take a screenshot of this chart. The correspondences between the hyperbolic and the circular trig functions. Now, so the hyperbolic trig functions are just like the circular trig functions, only they're on the hyperbola instead of on the circle, the unit hyperbola instead of the unit circle. So, well, what's not to like about that? Well, I guess it might be sort of unsatisfying, the fact that we don't have a good interpretation of what t is as opposed to theta, theta, we have a wonderful interpretation of, what's the hyperbolic angle. And we're going to get a good interpretation of that when we finish our hyperbola area problem, which I'm becoming less sure is going to be today, but it still could be, because we're going to dive right back into it, and we can probably finish it in time. So, back to the hyperbola problem. So, this is how you draw a hyperbola. You draw this straight line y equals x and y equals negative x for this branch, and then you make it asymptotic, so there's an asymptote there. Okay, so that's that, and we're trying to find this area. Of course, this curve, as I said before, this curve is y equals square root of x squared minus 1. So this, and this is, say, x right here. So a of x, this is a. A, the area of this region. So a of x, I'll write it up here in the corner, equals, a of x equals the square root, equals the integral from 1 up to x, the square root of 1 minus v squared dv. And so now let's do the hyperbolic trig substitution, the hyperbolic trig substitution of v equals cosh t. So that, of course, it's a fairly natural substitution if we think about the hyperbola and the meaning of hyperbolic trig functions. It's exactly what it is. But so then this implies that dv equals sine of t, sinh of t dt. And so then this integral right here becomes integral 1 up, or integral 0 up to cosh inverse. I'm not gonna carry around the cosh inverse because it's not the most pleasant to carry around. Or to write repeatedly. But so it's the integral from 0 up to cosh inverse of t of square root of 1. Sorry, I wrote this all backwards. V squared minus 1. So the square root of cosh squared minus 1 cosh squared t minus 1 times sinh t dt. And of course, this expression right here is sinh t. It would be plus or minus sinh t, but it's plus because we're up here where y is positive. So integral from 0, I'm going to drop the bounds like I said. So integral of sinh squared t dt, and now we're going to do exactly the same trick that we did on the circular problem before, which is, this is going to become integral of 1/2 of 1, in this case it's going to be reversed, of cosh of 2t minus 1 dt, right? Because cosh t, this is just like with the circular trig problem. So cosh 2t is cosh squared t plus sinh squared t, and 1 is cosh squared t minus sinh squared t. So when we subtract, the cosh squared t's cancel and the minus becomes a plus. So then we get 2 sinh t, and then we do a half, and then we have sinh squared t as stated. So, and this is gonna equal, we can pull the 1/2 out to the front, and So this is going to equal, I'm going to put the bounds back in now, 0 to cosh inverse of t of cosh 2t minus 1 dt, and the 1/2 times minus 1, so that's going to become 1/2 of at the top, minus 1, you just integrate minus 1, and this just becomes cosh inverse of t. So minus cosh inverse of t, and then plus the integral of this, which, as stated before, is going to be, we're going to have another 1/2, so it's 1/2 out here, and then we get another 1/2 from the 2 composed inside. So we get a 1/4 integral of cosh t, which is sinh t, 1/4 of sinh 2t, and then I'm going to use the evaluation bars, 0 to cosh inverse of t. And this is again going to be very much like the circular trig case. We use this identity that sinh 2t equals 2 cosh t times sinh t. So we're going to have 1/2 of minus cosh inverse t plus 1/4 times 2 cosh t, which is going to be the, sorry, I've been writing cosh inverse of t. I should be writing cosh inverse of x all along. Cosh inverse of x. So 1/4 of 2x times the square root. So this is the cosh t, where t is going to be cosh inverse of x, and then this is sinh t, and so we can write this all out. 1/2 of x square root of x squared minus 1 minus cosh inverse of x. So now, for what I want to say next about this example, I'm gonna change the picture slightly to make it easier to draw what I'm trying to say. So let's move x over a little bit here, and then A is going to be this area. And so I'm going to draw in here a straight line connecting this point, and then this little area right here, the area between this point and this ray, the straight line coming from the origin reaching this point, contained between here and the axis. So why am I doing this? So okay, so in a circular angle, it can be thought of as the arc length along the unit circle, the length along this curve, right? So if you go all the way around, it's 2 pi. If you go halfway around, this is just pi. A quarter of the way around is pi over 4, and then if you're like just over here, this is pi over 6, right? It's pi over 2 divided by 3, pi over 6. So it's the length along the way, but you could also think of it as area, because it's just cutting off the circle. And as I commented earlier in this lecture, and as it's quite obvious, with the area formula, area of the circle is pi r squared. The area, so if the unit circle has area pi times 1 squared, it's just pi. So you could also think of it as an area. So pi over 6 is the area contained here between the circle, the x-axis, and a ray reaching out to that point, which is, analogous to this quantity over here. So I'm going to propose interpreting this quantity here as a hyperbolic angle. And so what this quantity is going to be is it's going to be the area of this bigger triangle minus a. So let's call the area of this whole triangle here t. So, and let's call this capital. Actually, I'm going to call the area of the whole triangle b because t is a loaded word. So the area of this whole triangle is b. B is the area of the triangle, and let's call this hyperbolic angle for now. Let's call it capital H. This area in here. So this area is capital H. Area of that little red region. Can you see the capital H in there? Yeah. I guess you can't really see the A very well. There's an A here. Okay, so then we're going to call the area of the whole triangle, what did I say, B. So B equals A plus H. And what we're really interested in is H. And B is easy to compute, right? It's just a triangle. So this whole rectangle here, this rectangle is just going to be x times the point on the hyperbola, and B is going to be 1/2 of this whole rectangle, right? Or you could just think of it as a triangle. The formula for the area of a triangle is 1/2 base times height. So B, the area of B equals base, which is x, and then y. Well, y equals the square root of x squared minus 1. Equals x, and the square root of x squared minus 1 all times 1/2. So let me just rewrite this then. So replacing b in this, so a plus h over here. B equals a plus h, and b is 1/2 times x times the square root of x minus 1 equals a plus h. So that means that h, which is why we want h equals a minus 1/2 x times the square root of x squared minus 1. But then if we plug that into the formula over here, that means h equals a, which is this whole thing minus this term right here, which corresponds to this. So we get, sorry, I wrote this backwards. It's 1/2 a equals b minus h. We get 1/2 of x times the square root of x squared minus 1 minus a. So when we subtract off this term, that cancels with this term, and we're just left with minus 1/2 of minus cosh inverse of x, which is just going to be positive 1/2 cosh inverse of x, which is t in the little t in the as the parameter to the hyperbola parameterized. It's t where t over 2, where x equals cosh t, and y equals sinh t. So it's the parameter in the hyperbola in this parameterization, only now it's divided by 2. And that division by 2 is sort of a little bit unsatisfying, because it seems like it'd be nice if it was exactly the same idea as this. I mean, I guess you can think of it in a lot of ways. I mean, maybe it's because there's the other branch over here as well, and so h is going to be like, it's going to be doubled because of that or whatever for the hyperbolic angle. I don't know. I don't know if that's a satisfying interpretation or not. You can decide. But so t is proportionate to this hyperbolic angle, and it's usually just called t. It's usually just called the hyperbolic angle. So yeah, so now we have an interpretation of what t is, which is kind of nice, I think. Because oftentimes with parametrized curves, t is just something in some other domain, but now we have an area interpretation of it. So I think that's about time for today. Tomorrow or next week we will return to talk about integration by parts, which is going to be like reverse engineering the product rule.